So I'll be discussing the time complexity of counting sort. First is a big notation. The time complexity of counting sort is the n plus k, where n is the number of elements in the input array and k is the range of input values. This efficiency is achieved because the algorithm does not perform element comparisons. So counting sort has a time complexity of O, which is the n plus k. N is equal the number of items to sort. K is equal range of values like 0 to 100. For discussion, counting sort is especially efficient for small or fixed ranges of integers. However, when the range is k is significantly larger than n, the algorithm can become efficient in terms of both time and space. As such, its usage is best suited for bonded datasets like grading systems, bucket size data, or character sorting in lexicographic tasks, which counting sort works really well. When the range of numbers k is small, but if k is much bigger than n, like sorting 10 numbers from 0 to 1 million, it uses too much time and memory. Well, it's best used for sorting grades, sorting characters, like in text, buckets of data with known ranges. Now, I'll be discuss the algorithm simulation. The real-world simulation, a practical simulation of counting sort, can be demonstrated in grading system. For instance, consider an educational institution processing thousands of student grades 0 to 100 scale. The algorithm allows fast and stable sorting of these scores for generating ranked lists. Imagine a school sorting thousands of grades from 0 to 100. Counting sort is fast and accurate in ranking students because it works well when values are in a small range. Now, the test cases of this counting sort are like sorting student grades from multiple classes, organizing voting tallies for election where votes are limited to a known number of candidates, counting and sorting frequency of the ASC2 characters in text processing. The next is the result and observation. The simulation showed that counting sort can efficiently process and sort large data sets when the range is small. It is stable and preserves the relative order of equal elements, which is valuable in multi-key sorting scenarios. To the results and observations, fast for large lists with small value ranges. Stable, meaning it keeps the order of equal items. Helpful when sorting by multiple criteria. So it's great for specific tasks, but not always the best for general use.
So today I'm going to report the performance evaluation. Based on our test, we focused on two key aspects: runtime and memory usage. When handling up to 10,000 grade entries, counting sort consistently outperformed comparison-based algorithm like quicksort and merge sort in terms of speed. Its linear time complexity 0n plus k makes it especially efficient for datasets with a limited range of values. So to properly assess performance, we used quicksort and merge sort as benchmark. We measured the execution time and monitor the peak memory usage while sorting datasets. This helped us to observe how well counting sort scales with larger inputs and different value ranges. So based on the result, it clearly showed that the counting sort is highly effective when the range of values represented by k is not significantly larger than the number of elements n. However, its performance dropped when faced with datasets containing very large value ranges. Why? Because the algorithm needs to create a count array large enough to span the entire range, which leads to high memory consumption. So in short, counting sort is ideal for sorting large number of items within a small predictable range, but it's not the best choice when memory efficiency is a concern.
Algorithmic strengths of a counting sort. Counting sort is fast, stable, and suitable for real-time applications with constrained integer ranges. Its linear time complexity gives it a distinct advantage over comparison-based algorithms under ideal conditions. Just like quicksort, so under quicksort and counting sort will take the win as it is more efficient and stable algorithmic sequences. So limitations and challenges. Counting sort's efficiency degrades as the range of input values increases, leading to excessive memory usage. It is also not suitable for sorting floating point numbers or large range datasets without modification. So one of the challenges of using a counting sort is it cannot be applied to a wide variation of datasets just like a million or more than that, as it can just use the smallest, or it is more stable on the minimum side of 1,000 or below, or it won't reach until a million for it to be stable.
This is the comparative analysis of our algorithm, which is the counting sort, and I will be comparing it to the bubble sort. I will be talking about the types of algorithms, what they are, the time and space complexity, and the stabilities, and when to use them. So, algorithm type. Counting sort is a non-comparison based sorting algorithm that uses a counting array to sort elements. So self-explanatory that means it doesn't compare numbers to each other. Instead, it counts how many times each number appears, then arranges them using the correct array to sort the elements. So the bubble sort. The bubble sort is a comparison-based sorting algorithm that repeatedly swaps adjacent elements if they are in the wrong order. So it looks at two numbers next to each other and swaps them if they are in the wrong order. It keeps doing that again and again until everything is sorted. So for example, I have an array of 3, 1, 2. It swaps out the 3 and the 1 because 3 is higher than 1. So now it's 1, 3, 2. So it swaps, then it swaps the 3 and the 2 because 3 is still higher than 2. So that's it. So the time complexities. The counting sort has a time complexity of O n plus k, meaning that the n is the number of times you are sorting, and the k is the biggest value, meaning the range. So if you are sorting like 5 numbers and the highest range is 95, you need to add up those two numbers, so it takes about 100 steps. So for the bubble sort, it is a O n to the power of 2, so it's n times n. So for example, if you have 10 items, you might do up to 10 times 10, so 10 times 10 equals 100 steps, so it's gonna take you about 100 steps. But if you have like 100 items and times that with 100, it takes 10,000 steps. That's why bubble sort is much slower and has a bigger time to process if it uses the big lists. So the space complexity, or how much extra memory in the algorithm uses. So the counting sort uses OK space. That means it needs extra memory to store the count of each number in the range. So if you're sorting numbers from 1 to 500, you'll need space for 500 counts. Bubble sort uses 0, 1 space. That means it doesn't need any extra memory. It just sorts using the original list by swapping the values, because it only swaps the values. It doesn't add anymore. So let's move on to stability. Both of the algorithms are stable. So, which means if two numbers are the same, they stay in the same order they were before sorting. So, This is useful when sorting things like students with the same scores in a test, like that. So in the use cases, best for sorting in range, counting sort is best when you are sorting integers in a small range, like for example like in the stability, the test scores from 0 to 100. It doesn't work well with decimals. It only works with whole numbers or a huge range like 1 to a million. It doesn't work well with that. So the bubble sort is not really used much in real life in apps because it's slow, but it's good for learning and understanding how the sorting algorithm works in a simple way. But it also works fine with very small data sets.